Okay?
All right. The first one is tangent of the inverse cosine of 1/3.
All right. This is an angle, right?
Right.
Okay, let's write that angle right there. It's an angle whose cosine is 1/3.
Right.
So I can dimension that. This has to be 2√2 using the Pythagorean theorem. Square root of 9 minus 1, square root of 8, which reduces to 2√2. So, in other words, if the inverse cosine of 1/3 is equal to an angle, then the cosine of that angle is equal to 1/3. So just
Right.
from this information, I can construct that triangle.
Okay.
Now, what's the tangent of theta? Let's let that be theta.
Uh, 2√2.
Exactly.
Okay.
It's as simple as that.
Okay.
What else you got?
Cotangent of inverse sine of negative root 2 over 3.
Again, draw a triangle and let this be theta. In other words, the inverse sine of negative root 2 over 3 I'm going to call theta. Okay? Now, let's ignore the negative sign for just a second.
Okay.
Dimension my triangle.
The hypotenuse is 3. And the side opposite of theta is root 2.
Which makes this square root. You want to get good, you want to get fast at these.
Right.
When you're solving for the short side of a right triangle and you know the other two sides, the short side is the square root of the hypotenuse squared minus the other side squared. Well, that's the square root of 7.
Right.
So that's what this is, the square root of 7. Now, the negative sign, if you were to put this into your calculator, it's going to give you the fourth quadrant angle. So theta is going to be the same. It's just in the fourth quadrant.
Right.
When we take the cotangent of theta, what do we get?
Negative root 7 over root 2.
Yeah, first from the triangle we get root 7 over root 2, and we know it's in the fourth quadrant, and cotangent's negative in the fourth quadrant, so I know it's got to be negative. It's not negative just because of the negative sign in front of the sign.
Right.
It's negative because this tells us it's fourth quadrant. And notice that it's not third quadrant. In other words,
Right.
when you're writing these inverse trig functions, sine positive first quadrant, negatives fourth quadrant. Even though the sine of a third quadrant angle would be negative. So whatever theta is, if I make that the reference angle in the third quadrant, I'm going to get minus square root of 2 over 3. But it's very important here to know the principal quadrants that you get.
Right.
I know this is fourth quadrant. I've only got two choices. If this was a positive number, it would be first quadrant. If it's a negative number, it's fourth quadrant. It's negative, therefore it's fourth quadrant. And cotangent has to be negative in fourth quadrant. That's why it's negative. And you don't have to worry about rationalizing these, right?
No, not at all.
Okay. What else you got?
The cotangent of inverse cosine of negative 3 over 3.
Negative 3 over 3?
Yes. Oh, sorry, negative root 3 over 3.
Notice that in the previous two problems, we never did know what theta was, right?
Right.
You don't have to know what theta is. All you have to be able to do is dimension all three sides of that triangle. Well, give me two of them.
The side adjacent to theta is root 3. And the hypotenuse is 3.
Which makes the opposite side
Root 6.
Which quadrant are we in?
Quadrant 2.
Good. What's cotangent in quadrant 2?
Negative.
So what's the cotangent going to be here of theta?
Negative root 3 over root 6.
Yeah, I come up with the number first, and then I worry about the sine. Second quadrant, cotangent's negative in second quadrant. Again, it's not because of the negative sign in front of that cosine. It's merely because this tells you the quadrant. Sometimes, by being second quadrant, if they wanted the sine of that instead of the cotangent, well, it's going to be positive. Sine is positive. In other words, even though I still have the negative sign in front of the root 3, the fact is that the sine is now going to be root 6 over 3, and it's positive because it's second quadrant.
Okay.
Okay? So the negatives don't always go together. Just the first two problems we had a negative argument, and it ended up being a negative answer. But not always the case, as this shows right here.
Right.
What else?
So the next ones are graphing.
Okay.
Y equals 3 times cosine of x.
Here's cosine of x. Hold on. There's cosine of x.
Right.
And that static starting to leak back in, so I guess that wasn't a total solution. But it's tolerable. It's acceptable on my end. I don't know if it is on yours or not.
It's okay.
What's the 3 doing?
It's a vertical stretch.
So where am I going to start my curve in red?
Positive 3.
So it's going to go from 3 to minus 3. And the period's not any different. So it's still got to go through that point, that point, that point, back up to that point. And it's got to go through this point right there. In other words, I still quarter it up, and now the curve's going to look. Still going to look like a cosine curve, but it's going to be vertically stretched.
Right.
Okay?
So then, if that were 3 times cosine of 2x,
Let's do that one. The 2 affects what? In other words, here, let's go through this the way we should. A equals 3, B equals 2, C equals 0, and D equals 0. You with me with these letters? I know you guys use something a little different, don't you?
No, that's what we use.
Okay, that's what you use? Okay.
Yes.
So B is 2, that makes the period what? B never tells you much directly. It merely allows you to calculate the period.
Right. So it's a period of pi.
Okay. Now we can graph it. So I know it's going to start. There's no horizontal shift. So it's going to start there. It's going to go out to pi. Got to quarter it up. Pi over 2. Pi over 4. 3 pi. I know it's going to go up to 3 and down to negative 3. And now the way I've always done these that I think works the best is if you plot 5 points and then connect the dots.
Right.
Okay. Well, you start your cosine curve at its maximum value, goes down through the x-axis the first time through the first quarter point, goes down to the minimum value at the next quarter point, comes back up through x-axis on the third quarter point, fourth quarter point's where it ends, make it look like a cosine curve. But the only difference between this and the previous one is the period. This was all between 0 and pi. Previous one went from 0 to 2 pi because it didn't have a coefficient in front of the x. In other words, if you have a b that's not 1, then it changes your period.
Okay.
Okay? What else?
So the next one's a tangent graph. It's 2 times tangent of 3x.
And these are a little different. Sinusoid function, the title, means you got to have either sine or cosine in it.
Right.
You can still do transformations of tangent curves, though. In other words, if I draw my tangent curve, my basic tangent curve, got these asymptotes, goes from minus pi over 2, pi over 2, which makes its period what?
Pi.
So that's y equal tan of x. Well, this 3, in other words, I can still say a is 2. In other words, I'm going to have a vertical stretch on this curve. But the fact that b is 3, and I'm not even sure it's fair to call that b, but there's a coefficient of 3 in front of the x, which makes the period what?
2/3 pi.
Actually, with tangent, the period is pi, not 2 pi.
Okay.
The period is not
right. Oh, gotcha.
b, it's pi over b.
Okay.
So with tangent, it's always pi, tangent and cotangent. Their period is pi. All the other 4 have a natural period of 2 pi. But because this has a period of pi, then its period is going to be pi over 3.
Okay.
Okay? Now, in order to get a period of pi over 3, that's the fact that that's over 1 means it's a horizontal shrink. Right?
Right.
This is a vertical stretch, the 2. But the 3 is a horizontal shrink. What that means is between my new asymptotes, I have to have a period of pi over 3.
Okay.
Hold on, let me do this properly in red. There's one asymptote. There's another asymptote. That asymptote, if my period is pi over 3, then that must be going from minus pi over 6 to pi over 6.
Right.
That would give me a period of pi over 3.
Okay.
Now, if I just had y equals tangent of 3x, it would look something like this. Gotta have smooth hands to draw these. So you get the picture?
Yeah.
Okay. Now, in blue, I'm going to plot y equals 2 tan of 3x, which is a vertical stretch of the pink curve. And a vertical stretch of the tangent curve tends to, instead of doing this, it's going to do that.
Right.
So if I draw that, I'm going to draw it between those same 2 asymptotes. And the one point that I know about tangent is the tangent of pi over 4 normally is 1. Here to explain this. One thing they don't draw on the tangent curve is this point, which I always have found peculiar. In other words, this is just the tangent curve. It's supposed to go through 0, heads up towards infinity. But, and this is normally pi over 2, minus pi over 2. But there's also a pi over 4. Well, we all know that the tangent of 45 degrees is 1. So that point right there is 1. Don't know why the regular tangent curves don't show it like this. They should.
Okay.
Because if this is y equal tan x, then I want to do y equals 2 tan x. Well, where's this point going to be?
1 up.
Yeah, it's going to be twice as far away from the x-axis. That's the way I tend to think about it. In other words, this point that I've circled is actually going to come right there at 2. So now, if I draw the same curve, it looks more like this.
Right.
And that's what a vertical stretch of the tangent curve is going to do. It's going to make it narrower. It's going to have a similar effect as a horizontal shrink. And in the problem you gave me, it had both. It had a horizontal shrink by a factor of 3 and a vertical stretch by a factor of 2. And I'm going to go. We'll just hope my phone lasts another half an hour.
Okay.
If I lose audio with you, I will go get my charger, plug it in, and be able to continue our session. Oh my God. Really does feel exactly like if you were scratching your fingers on the wall or on a chalkboard and you stop. All of a sudden the calm, the quiet is unbelievable. All right.
Yeah, that's weird. It gets really loud at some point.
It really does, and it just kind of grows. When you first start, it's just hardly noticeable. But boy, after a while, as it grows, you don't notice how bad it is until I call you, and then I notice it. But anyway, I don't think we'll lose the call. I don't think it'll go through the battery in a half an hour. But if it does, just hold on for 30 seconds. I'll go in and get my charger, plug it in, and I'll call you back.
Okay, for sure.
Okay? I just hope I'll know I guess my phone will start warning me as the battery gets low. All right, what else you got?
Y equals 3 cosecant of x.
Key thing on all of these is to be able to draw the non-transformed curve.
Right.
Okay? Cosecant's reciprocal of what?
Sine.
So it's got to sit on top of the sine. Just in light blue here, I'm going to draw a sine curve. It's just a regular sine curve. So that would go from 1 to -1. And notice that because cosecant is the reciprocal of sine, wherever sine is 0, I'm going to have a vertical asymptote because I'm going to be dividing by 0.
Right.
So I got one there. I got one over here. And in fact, I have one every pi. I also have one that is the y-axis. Okay? And if I want to draw my cosecant curve, I know that when sine is equal to 1, cosecant's got to be equal to 1. So they both have to share that point right there.
Right.
And that's how I know how to draw it, is that it sits on the peaks. When cosecant, or when sine is equal to -1, cosecant's equal to -1. They both have to share that point. Now, I can go in and erase the sine curve because I don't really need it. I just used it kind of as a reference on how to draw this cosecant curve. Unfortunately, this eraser doesn't do what my last eraser did, which was erase the whole line right away. So anyway, what I have there is y equal cosecant x. The 3 does what?
It vertically stretches it.
Okay. So this point that's now at 1, this point right here, where's it going to be on the stretched curve?
At 3.
Okay, so if we go up to 3, and it's going to go down to -3, and instead of looking like the blue, it's not going to look a great deal different, but it actually is.
Separated a little bit.
Yeah. So it's kind of like that. In other words, when you do a vertical stretch of the cosecant or secant curves, they add separation between their peaks.
Okay.
Like I've shown there. The shape doesn't change a whole lot. In other words, if I just drew a curve and drew a cosecant curve, you're not going to be able to tell by looking at the shape whether it's been stretched or not. If you see that it's only going down to 3 and it's only going up to -3, well, then you know it's been stretched by a factor of 3. So as long as they give you some points like that and that, then if they showed you the curve, you'd be able to figure out the formula, the equation.
Okay.
Okay?
So what's the equation to calculate the period for cosecant?
Cosecant's the same as sine. In other words, the period of what I drew there is 2 pi.
Okay.
For one full cycle. Notice that this is not one full cycle, that's half a cycle.
Right.
This is the other half. So from start to finish, and then it starts again over here.
So
okay.
Each
so
counts as half of a
yes, the full period of cosecant is normally 2 pi. And so if you had something like 3 times cosecant of 2x, you would find the period in the same way you would if it was sine. In other words,
okay.
b really is 2, and b is 2 pi over the period, and making the period 2 pi over b, so the period would become pi for that.
And so then
The only one that's different is tangent and cotangent. Tangent and cotangent, this formula is pi over the period.
Right.
But the other 4, it's always 2 pi over the period.
So if the period were pi, the asymptotes would be twice as frequent?
If the period were pi, I would label that pi right there. And then I would split it up. That must be pi over 2. And that's all I need. I don't really need to quarter it. Maybe I need to quarter it to figure out where that minimum's going to come.
Right.
That point there. And that's 3 pi over 4. And that tells me where that point's going to come. So it's basically the same as what you do with sine and cosine. Exactly the same. You still have to quarter it up from its starting spot to its ending spot. As long as you know the period, you know what this label is, quarter it up, and that'll tell you everything you need to know to graph it.
Okay. So how would you write the domain and range?
Okay.
Of a graph like that?
Well, it's a little tricky because the domain is no longer all real numbers, but it's close, right? In other words, the domain is all reals except what? X can't be 0. If we're looking at if we're looking at a regular one, in other words, my gray one,
right, pi,
where that's pi, that first asymptote is pi, the second one is 2 pi, well then I cannot have multiples of pi. And that is expressed like this, using the letter n, where n is all integers. In other words, how do I interpret that? It means x can be any number on the number line, except it can't be 0, and it can't be, in fact, I don't even need the 0, I just need the n pi. It can't be n pi, where n goes from negative infinity to positive infinity, integers only.
Okay.
So you wouldn't be able to be 0, you wouldn't be able to be pi, you wouldn't be able to be 2 pi, you wouldn't be able to be minus pi, you wouldn't be able to be minus 2 pi. Each of those defines the vertical asymptote. And remember, just like polynomials, you can never cross a vertical asymptote. That's why it cannot be any of those. Now, let's talk about tangent for a minute, because tangent's a little different in how you define the domain. Just a second, I seem to have lost my cursor here. Get down, there we go. In other words, because the tangent goes from minus pi over 2 to pi over 2, if I were to describe the domain, and then of course it repeats every pi, right? So here's what the tangent curve looks like. Doesn't cross that asymptote, just approaches it. That's 2 periods of the tangent curve, incidentally. That's not 1 period, that's 2. Okay? So the domain, again, is all reals except, well, it can be 0 now, but it can't be pi over 2 plus n pi. So that's the way you would write the domain for tangents. And notice how that works. In other words, when n is 0, well, then it can't be pi over 2.
Right.
When n is minus 1, it can't be minus pi over 2. When n is 2, then it can't be 5 pi over 2. In other words, this is 3 pi over 2. The next vertical asymptote is going to come at 5 pi over 2. And so basically what this is defining is all of your vertical asymptotes. And this is the only way to define those vertical asymptotes. Pi over 2 plus n pi.
Okay.
And this is really the first place where you've had to use this n in describing a domain. And the first time they teach you about it, they will qualify and say n is equal to integers. They'll somehow describe it. I'm not sure exactly how they'll describe it. All integers. Okay, including negative ones. And if n is 0, then it's just, you can't be equal to pi over 2.
Right. Okay, gotcha.
But the way this works is n is presumed to be all, how would I talk about that? All integers from negative infinity to infinity. That's what n is.
Right.
And it's all of them. It's not whatever one you pick. In other words, n isn't 3. N is, if we deal with positive ones only, n is 0, and then n is 1, and then n is 2, and then n is 3, and so forth and so on. That's the way this works. N is a dynamic variable.
Okay.
And it won't always be n. Sometimes they use k. In your class, they might use k. But nothing changes. It's still all integers. And the tangent one's a little tricky because I had to have this first part. The cotangent one is easy. The domain of cotangent is all reals except n pi. I don't need the first part because the first asymptote comes at 0.
Right.
Whereas with the tangent curve, the asymptotes don't come at 0. They come at minus pi over 2, plus pi over 2, 3 pi over 2, and so forth. And the only way to describe that sequence of vertical asymptotes is by this designation up here. Okay. Have they taught you this yet? Or did you just ask it out of curiosity?
No, they haven't taught us yet. I was just wondering.
They will if they ask you about domain. If they ever ask you about domain of any of these trig curves that have vertical asymptotes, then they have to get into this notation.
Okay.
And they will explain it to you, hopefully the same way I just did.
So then for this graph, the range would just be negative infinity to infinity.
Correct. In other words, the range for tangent is all real numbers. Whereas the range for sine is -1 to 1. And the range for cosecant is greater than 1 or less than -1, but nothing in between.
Right. And so the range for cosecant is -infinity to -1 with a bracket?
Correct?
Okay.
In combination with?
Union +1 to positive infinity.
Also with a bracket around that one.
Right.
Because it can be that. In other words,
right, it touches the sine curve.
Yeah, it can be 1. Sure. Okay, what else?
Now secant. Y equals 2 secant of 3x.
Well, they're not making these easy for you.
No, I don't like those 3's.
Well, that's because it makes it hard to quarter it up.
Yeah.
What's the period going to be of secant?
Pi/3.
The period of secant is 2 pi. So the period of this function is going to be 2 pi over 3 over b. b is 3 in this case.
Okay.
Okay? So that's the period, and the easy way to do it is just to pick a point out here and call it 2 pi over 3. And we'll draw our graph around that. Instead of labeling that 2 pi and then having to come way down to a real skinny graph to go to 2 pi over 3, I do it this way. It gives me room to work. Okay? Now, chop it up. You always got to chop it up. What's that point there? Just divide that by 2.
1/3 pi.
And this point?
Pi over 6.
Okay, not so bad then. What's this point? Let me tell you a better way to do this when you're quartering it. Leave all your denominators the same. Here's why.
Okay.
If I make this 2 pi over 6, which is the same as pi over 3, and I make this 4 pi over 6, which is the same as 2 pi over 3, now it's real easy to know what that has to be. What's halfway?
3 pi over 6.
3 pi over 6. So
Which is just pi over 2. Okay.
Right, but sometimes it's better not to simplify them. If you don't simplify them, it's easier to quarter it up. Okay? Now, the secant sits on the top of the cosine curve. Okay? So the secant's got to look something like this. With this point being what for our function?
+2.
And then on the other end, in other words, here, let me think for a second. If I still feel more comfortable if I draw the cosine curve first, which let me do. Here's what the cosine curve's going to do. Right? In other words, that would be the cosine of, that would be 2 cosine of 3x. In other words, it would go to 4 pi over 6. And it would be quartered up in this exact way. Well, the thing about the secant is wherever cosine is 0, I've got to have a vertical asymptote. So I'm going to have my vertical asymptotes through pi over 6. This is negative pi over 6. And then on the bottom, it's going to look, I'm going to have another asymptote here, next place, the cosine would be 0. And so it would look like that, and that would be minus 2. And that's one full period of your function.
Okay.
And that's the way to do it. Always start with the period. In other words, don't start with the 2, start with this. And see if you can draw that, and then you can actually just label it 2 and minus 2 instead of 1 and minus 1. In other words, it's almost easier to not label the vertical axis until you've drawn it. But
okay. So then for the domain, it would be all real numbers not equal to pi over 6 and pi over 2, or pi over 3.
plus, need a plus sign.
Right, okay.
Where's the next vertical asymptote?
3 pi over 6.
Which is how much? That is 2 pi over 6 away. So it's n times 2 pi over 6, which is pi over 3.
Okay.
So that's how you would define it.
Okay.
Notice that, and you can always check this out by just, well, when n is 0, I got an asymptote at pi over 6, I do. When n is 1, I got an asymptote at pi over 6 plus 1 times 2 pi over 6, that's 3 pi over 6, I do, and so forth and so on. So once you come up with this domain, check it. At least check to make sure that it gives you your first couple of asymptotes in the right location. Okay? Tell me when you're ready to go to the next one. I don't want to erase this until, because you might have more questions about this one.
I think I'm good.
Okay.
Okay, so can you show me the graph for inverse cosecant? There's y equals inverse cosecant of x.
Okay, inverse cosecant. Wow. Yeah, I think I can. That's not an easy one. Y equals inverse cosecant of x. Well, just like we're going to have to restrict the domain. In the same way that you have to restrict the, let's talk about y equals inverse sine of x. Okay. Normally, to take an inverse function, you just rotate it about the line y equal x. Okay. But if I did that here, I would end up with something that looked like this. That's not a function. Doesn't pass the vertical line test.
No.
So you've got to restrict, whenever you take the inverse and it does not pass the vertical line test, then you know that you have to restrict the domain.
Okay.
Okay,
right.
And what they restrict it to is, for the sine curve, they restrict it from minus pi over 2. Hold on. In other words, if I want to find the inverse of the sine curve, I restrict the domain from minus pi over 2 to pi over 2. And I erase everything else. And the reason is that if I restrict it, that's 1-to-1 now, right? And in order to have an inverse function, you have to have a 1-to-1 function to begin with. And these are functions. These inverse trig functions are functions. So we have to make sure they're one-to-one functions. And if I take this sine curve that I've drawn and do the inverse of it, it's going to look like something like this. Oh, man, what happened? I got to figure out this new program a little bit, but it's going to go through that point there. Something like that. Okay? So the red curve is y equal inverse sine. Now, you're the first person in 8 years that's ever asked me to graph the inverse cosecant. So I'm going to assume that the restriction is the same. It's got to be. So we're still going to restrict it from minus pi over 2 to pi over 2. Well, in blue, let me draw the cosecant curve. Which is going to look like something. It's on the peak and the valley.
Okay, right.
Okay, only I'm going to restrict it to minus pi over 2 to pi over 2.
Right, so it passes the horizontal line test too.
Well, right, that's one-to-one. So let's take the sine curve I drew out of there. Oh, I hate this erase feature. The only reason I'm using this new program is because my erase button stopped working on my other program, and it won't erase to the right either. So now I've got to take this blue line that you see and reflect it over that red line. Right, and that will represent the inverse. Now let's see what that's going to look like. I'm not good at doing this. Let's see, first of all, that comes down. It doesn't curve back up. It goes, goes just to there.
Right.
So if I reflect that, something like that, the black, does that look like a reflection of that blue?
Yeah.
Yeah, and on the same thing on the other end. In other words, if I reflect that, I get that. So
then the x-axis becomes the asymptote, or asymptote?
Yes.
Okay.
So there's your inverse function, and as in all inverses, your domain becomes your range, and your range becomes your domain. So whatever the domain was of the cosecant function, that's now the range of the inverse cosecant function. And notice what that range is. It's not between minus pi over 2 and pi over 2. It doesn't show up anywhere in there. So the range gets changed. It's definitely true that the domain and ranges switch.
They're switched?
They always switch when you talk about inverse.
Right, okay.
Okay? Whatever the x-coordinate was becomes the y-coordinate. Whatever the y-coordinate was becomes the x-coordinate. Whatever the domain was becomes the range. Whatever the range was becomes the domain. So the question is, how would I draw a second period of this? Which is, I'm not sure how to answer that because I've never done it. I don't think they're going to ask you to do it.
I hope not.
Yeah.
Is it possible with the restricted domain then?
Well, yes.
If you were to do the inverse of.
No, you're right. You're right. If I were to do the inverse of inverse, yeah, if I did inverse sine, it only goes between minus pi over 2 and pi over 2. It doesn't go anywhere. It doesn't have a second period.
Yeah, if you did it
There's no second periods for these inverse functions. There's one period only, and this is it, the way I've drawn it. If I erase some of the stuff I used to emphasize it. In other words, that's what it's going to look like. I don't know where that came from, but I don't think that's there either. So something like that. Only it comes up and goes flat here. I don't think it curves back around. But
what's the mathematical significance of the inverse graph relative to the original?
To reflection over the line y equal x. All inverses are, including calculus. The difference between differential calculus and integral calculus is one is just the inverse of the other, and it's all inverses are reflections over y equal x.
Okay.
Including, let's take one that you're a little more familiar with. Let's take this function right here. Notice that I have a problem with this function.
Right.
If I reflect that over the line y equal x, I get a horizontal parabola, which is not a function. So if I want to talk about the inverse of this function, I've got to restrict the x's to be greater than or equal to 0, which is just this part of it.
Right.
And when I reflect just that part of it, I get, which is the same as the square root function.
Right.
And the square root function is indeed the inverse of x squared. Yeah.
Okay.
Yeah. So I think you pointed this out once before when we were talking conic sections and we had the full horizontal parabola. You realize that the upper half of that parabola is the same as the square root function, and it is exactly the same. In other words, this part right here is the upper half of the horizontal parabola, but it's also y equal plus square root of x. The bottom half is y equal minus square root of x. Because when you actually solve this, you get plus or minus.
Right.
So that's how you get the horizontal parabola. But in order for it to be a function, it has to pass the vertical line test, so you have to get rid of that part there.
Right.
William, I got a 7 o'clock I got to go to, so I will let you go and talk to you next time.
All right. Thank you very much, Mr. Calendar.
You're welcome.
Good night.
You too. Bye-bye.